my direction, I get like 45%. Okay, well, it's a pleasure to be here in Morelia. I'd like to thank the organisers for inviting me to come and talk to you over the next 4 talks about infinite dimensional Teichmüller spaces. So there are going to be some slides for this talk, and if you have internet equipped things, but at the moment they're living here. So eventually, hopefully these will appear on the conference website. But for now, if you want to follow along and see what I missed, what I skip in my slides, then you can check it. This is an AF underscore, not AE. So the general theme of this series of talks is to talk about Teichmüller spaces, and in particular the sort of properties that hold whether or not you're considering finite dimensional or infinite dimensional surfaces. So the theory started, and a lot of the research is focused on the finite dimensional case. But it turns out a lot of the properties that hold carry over to the infinite dimensional case, and we'll talk about which ones do and maybe which ones don't. So there's a lot of very good texts which deal with the general Teichmüller theory, quasi-conformal maps, those sorts of things. So just very briefly, let me tell you some other very good books to look up. There's Alfor's little green book on quasi-conformal mappings. Gardner and Lakic have a book on quasi-conformal Teichmüller theory. John Hubbard has a very nice book on Teichmüller theory, currently volume 1. I suppose volume 2 will be appearing at some point, but volume 1 at the moment is very nice. Iriyoshi and Taniguchi also have a very nice book, and let me also mention there's a book of Plato, Univariate Functions and Teichmüller Theory, which is the first Teichmüller Theory book I learned some quasi-conformal maps and Teichmüller Theory from. Okay, so the rough outline for the next 4 talks is as follows. So today we'll probably just talk about quasi-conformal maps. So we'll motivate those, construct them, talk about them, give various definitions for them. These are going to be foundational when we want to start talking about measuring things in Teichmüller spaces. So then we'll define Teichmüller spaces, talk about some of their various properties, how you can put certain metrics on it, and give it the structure of a complex finite manifold. And we'll talk about various properties of it. Then we'll go on to talk about extremal maps. So these will be extremal quasi-conformal maps, and for which, if you want a good reference, you should look up the survey paper of Edgar Wright, and how extremal maps link to geodesics in Teichmüller space. Then we'll talk about bihomomorphic maps between Teichmüller spaces. And a bi-Lipschitz counterpart. So we'll talk more about that in the 3rd or 4th talk. And then my buffer slides, if I go really quickly. Will be on some recent work that I did with Kahn and Markovich on counting balls in Teichmüller space. And the reason it's the buffer slide is that really it's closed surfaces, so it's a finite dimensional thing, not an infinite dimensional thing, but hey, maybe I'll talk about it on Friday if there's time when we get there. Okay, so the first topic we're going to talk about is quasi-conformal mappings. Now I'm probably going to aim a little bit low here and maybe go fairly slowly. So maybe I'm just going to tell you things that everybody already knows. If that's the case, well, just enjoy being in Mexico, or if you've got jet lag, kick back and relax. Just, that's what it's going to be. So I come at this topic from complex analysis. So let's start with the topic from complex analysis, conformal maps. So what's a conformal map? Well, it's holomorphic. The derivative isn't zero. So if you look infinitesimally, what happens with a conformal map, then it's sending circles to circles. Let's put a small here. So in other words, what this is saying is that the derivative, if we view it as a mapping from R2 to R2, it's complex linear. So if we write down what the derivative is as a matrix, so the matrix representing, say the derivative at a point Z0, is going to be given by a scaling composed with a rotation through the argument of the derivative. And both these mappings are mappings which send circles to circles. So the derivative is indeed a complex linear map. So if we start here, what we want to do is generalize this notion. So instead of sending small circles to small circles, we want to send small circles to small ellipses. So small circles are now being sent to ellipses. Or, if we assume our mapping is real differentiable, then, well, this corresponds to the derivative being R linear. So the derivative isn't necessarily now going to be a composition of a rotation and a scaling. It might have other linear maps involved as well. But what we want to have is that we have a bounded amount of stretching. So we look at all the points in our domain and we see what the ellipses look like on small scales, and we don't want the ellipses to get too stretched over the domain. We want to have some bound on how much stretching is going on. So the only thing here is that we're assuming for the moment that our mapping is real differentiable. But this is not desirable. So we don't want to assume our generalizations are differentiable. So we want to allow other mappings to be quasi-conformal without requiring they be differentiable, and the reason for that is we will want some nice compactness properties. So we're going to want to be able to say that if we have a sequence of quasi-conformal mappings which all have the same amount of distortion, then they have some subsequence which converges to a limit. Whereas if you have differentiable mappings, then there's no reason to assume that the limit takes some limit in a pseudo sense, is going to be differentiable. So what we want is, well, let's just write down a definition and start from there. So we'll see there's actually a number of different equivalent ways of defining quasi-conformal maps. We're just going to start by defining them with the analytic definition. So let F from a domain U with U be a homeomorphism. Well, then we say F is quasi-conformal if and only if the following two properties hold. So we're going to want two properties. The first one deals with how regular the mapping is. So not every homeomorphism is going to have this sort of property right here. I've got my indices in the right places. What we want is F to live in some Sobolev space, which essentially just means that F has L2 integrable partial derivatives. And the second condition we want is a condition which encodes this bounded amount of stretching that's happening here. Well, we want there to be some small k in 0, 1, such that the z bar derivative of F is less than or equal to k times the z derivative of F almost everywhere in U. And the complex partial derivatives here are given by f sub z is the x derivative of F minus I times the y derivative of F divided by 2, and f sub z bar is f sub x plus I times f sub y divided by 2. Okay, so the regularity condition tells us that we have integral partial derivatives almost everywhere. It doesn't, however, imply that f in fact itself is differentiable. But condition 1 does imply that f is differentiable in the real sense almost everywhere. So it's nearly nice. We don't have to take this Sobolev space definition either. There are other equivalent regularity conditions we can take. So condition 1 is equivalent to f being absolutely continuous on almost every horizontal and vertical line in U. So being absolutely continuous on a line means that we can basically find some function and then integrate that function to give f. So on a line L, we can write f of x as the integral up to x of g d of t dt, the sum integral function g. So you can either take the Sobolev space definition or the absolutely continuous on almost every vertical and horizontal line definition. Now condition 2, which is the condition that encodes the bounded amount of stretching that we get, actually implies that f is sense preserving. So as an exercise, the Jacobian of f is the absolute value of the z derivative of f squared minus the absolute value of the z, so the absolute value of the z bar derivative of f squared, and because of condition 2, we get that this is greater than 0 almost everywhere. So we are sense preserving. So quasi-conformal mappings automatically, by the definition, are going to preserve the orientation.
What does sense mean? Or did you just define it? Or?
I just mean orientation preserving.
Oh, orientation.
That's all.
Oh, I see.
Okay, so given a QC map with this K, we define big K to be I want 1 plus little k divided by 1 minus little k, and this thing is going to be greater than or equal to 1. So given some number between 0 and 1, we can do this to it and come up with some number which is a real number, which is strictly greater than or equal to 1. And if we find a minimal little k, which depends on f, then f is said to be kf quasi-conformal, or just k quasi-conformal, where big K of f is given by this. So 1 plus little k of f divided by 1 minus little k of f. So what this big K does is it allows us to go back to the picture and tell us how much distortion we have. So a K quasi-conformal map distorts small circles by a factor at most k. Okay, so let's suppose we have a conformal map. Well, then f satisfies the Cauchy-Riemann equations. Which can be written in shorthand that the z-bar derivative of f is identically 0. So if the z-bar derivative of f is identically 0, then this implies that little k of this f is 0, and so that implies big K of this f is 1. So if you have a conformal map, it's dilatation. I should probably call this a dilatation. So if f is conformal, its dilatation is 1. And in fact, the converse is true too. So one quasi-conformal map is in fact conformal. So there's something to prove here, which I'm leaving out, and look at one of those fantastic texts I mentioned at the beginning, if you want to see proof of this fact. But what this is telling us is that the dilatation we have gives us a way of measuring how far away our quasi-conformal map is from a conformal map. So the dilatation on F gives us a way of seeing how far in some sense F is from a conformal map. So if a conformal map takes infinitesimal circles and sends into infinitesimal circles, and we have a certain amount of stretching going on from our quasi-conformal map, then the maximal dilatation tells us how much stretching we're getting is a way of saying how far away our map F is from being conformal. So as an example, how about we take the mapping which just stretches in the x direction, well, then that's taking any circle we draw like this, not just a small one, and stretching it in that direction, parallel to the x-axis. So, excuse me. If you want to find out what the maximal dilatation of this is, well, we can write f of z in the form, I think k plus 1 over 2 times z plus k minus 1 over 2 times z bar. And then if we work out what the z bar derivative of f is divided by the z derivative of f is, well, we get that the little k of f is k minus 1 divided by k plus 1. And then if we work out big K of f, we get some slightly notation dodgy thing, that big K of f is in fact k everywhere. So this is kind of our prototypical example of a quasi-conformal map that just stretches in a particular direction, and the amount that it stretches is going to be exactly the size of the maximal dilatation.
As a quick question, what goes wrong that we don't want to consider k being less than 1 in this example?
You can consider k to be less than 1, and it still will be quasi-conformal. It will still have the same maximal dilatation. It's just
1 over k. You want?
yes, sorry. Yeah. Just for no particular deep reason. So there are a number of different ways of defining quasi-conformal maps. Firstly, let's talk a little bit about modules of quadrilaterals. How long do I have, by the way?
You still have until 10.
10.
Around, I mean, plus minus epsilon.
So, the module of a quadrilateral, this is related to the Groth problem. Which is as follows. Suppose you have a mapping F from one rectangle to another rectangle. So R and R1, which preserves the vertices so here's R, here's R1, and we want to send the top left vertex to the top left vertex over here, and we want the same property to hold for the other three vertices. And what we want to do is find the map with smallest dilatation satisfying these properties. So if we're just given one rectangle R and another rectangle R1, and we want to map one onto another, we can do it conformally if we don't care about the vertices, just by the Riemann mapping theorem. But the Riemann mapping theorem allows us to send 3 points to 3 points that we prescribe, but here the problem is that we've got a 4th point that we also need to prescribe as well. So you can't actually find a conformal mapping which maps R onto R1 if the ratio of the side lengths of R and R1 are different. So you have to try and prove that if you haven't seen that before. Okay. So a length area argument, which I guess I'm not going to have time to go through at the moment, shows that the affine stretch of the form that I've just written off here f of x plus iy is kx plus iy solves the problem, and it solves it uniquely. So we can do some normalizing here by just dilating in the domain of the image, so we can assume this is 0, this is I. This is I plus alpha, and this is alpha, and then if this is 0, I, this is going to turn out to be I plus k alpha. K alpha. Again, I'm assuming k is bigger than 1, but less than 1 too. Well, this mapping here stretches this rectangle onto that rectangle, and if you have any other mapping, any other quasi-conformal mapping which maps this rectangle onto that rectangle and sends each of these 4 corners to their respective corners, then it's going to have larger maximal dilatation than this k here. So related to this, we can define what a quadrilateral is. Well, that's a Jordan domain with four prescribed boundary points. And what we can do with any Jordan domain like this is map it onto a unique rectangle of this form. So we can map and do it conformally too. into a rectangle with vertices 0, let's call it m plus I and I. So here's Q, and we can map it conformally onto R. So what we then say is that the module of this quadrilateral is the ratio of the side lengths, which, as I've normalized it here, is just m. So the module of Q is defined to be the m that we have here. So then we can define quasi-conformal mappings by how they distort the modules of all the quadrilaterals in our domain. So f from a domain U to f of U is quasi-conformal if and only if for all quadrilaterals Q which are contained in U we get the quasi-invariance that the module of f of Q is between 1 over k times the module of Q and k times the module of Q. Let's put a k here. So f is k quasi-conformal if and only if this double inequality holds for all quadrilaterals Q contained in our domain. So if we just have an affine stretch, then we're immediately going to get this weak point. I will not say quite as much about the other two definitions of quasi-conformality. Well, let's just say a function f from U to f of U is quasi-symmetric if and only if there exists an increasing function eta from 0 infinity to 0 infinity such that, so the idea of quasi-symmetric functions is to look at 3 points and see how mapping distorts the distances between those 3 points. So we take the absolute value of the ratio of the distance of the images between the image of x and the image of y and the distance between the images of x and z, and then this has to be less than or equal to our function applied to the absolute value of the ratio of the distances between x and y and x and z. And it turns out quasi-symmetry, or QS, is equivalent to quasi-conformality on open sets. So instead of starting with a Sobolev space definition, you can start with this definition, which involves how 3 points are distorted instead. Finally, let's have...
Does 0 have to be mapped to 0? I mean, or something about properness here? Or,
oh, you mean how we define...
yeah, or eta.
I guess it needs to be... Oh, this? Yes, it needs to be...
Sorry, it's 0.
Yeah, exactly. Yes, otherwise it's a little bit... Okay, so homeomorphism is quasi-conformal if and only we have the following property. Well, we want a constant h such that the following is true. Well, if we take a small circle of radius r, then the picture we had at the beginning of the talk assumed that this was going to be mapped onto an ellipse. Now, because f doesn't have to be differentiable, that need not happen, but it is going to be mapped onto something that looks like that. So what we can then do is, because it's a homomorphism, we can find the smallest circle which is outside our image of our circle of radius r, and we can find the largest circle which is inscribed inside. So this is f of the circle radius r. Again, doing it about 0 here, but it doesn't have to be about 0. Then the largest circle we can inscribe inside, we can call, we can give it the radius beta sub r, and the one outside we can call circle of radius alpha sub r. So what we want is for the ratio of these two things to be bounded uniformly as we send r to 0. So we want the limit as r goes to 0, oops, sorry, the supremum over all z in view, the lim sup as r goes to 0 of alpha r divided by beta r to be less than or equal to h. So the image of small circles of radius r are always going to be contained in some annulus which has bounded ratio of inner and outer radii as you send r to 0. So this is kind of a geometrical way of seeing what quasi-conformal maps do. Let's just say that it's kind of a remarkable result of Heinemann and Koskela that you can replace the lim sup here with a limit. So you just need a sequence of bars so that this holds to get quasi-conformality. Now we're going to want to focus on quasi-conformal mappings in the upper half plane H because of all the Riemann surfaces we're going to consider are going to be hyperbolic. Well, if f is quasi-conformal and f maps the upper half plane into itself, then f extends to a homeomorphism, let's call it f tilde, from the real line to itself. And it turns out that this homeomorphism of the real line is, well, behaved. In fact, f tilde is quasi-symmetric. And the converse is true too. So if we start with a quasi-symmetric map f tilde from R to R, we can produce quasi-conformal extensions of f tilde to a QC map f from H to H. So the extension isn't unique, there's lots of them. I believe the first was the Stirling-Alfors extension, which can be written down with an explicit formula. So it gives you f explicitly in terms of f tilde. And one that's much used these days is the Labial, or also called the barycentric extension, which is very useful because it is conformally natural. Which means if you take a quasi-symmetric map of the real line to itself and you pre- and post-compose by Möbius transformations, then the extension would agree to the extension you get if you, well, I mean, like this. The extension of A composed of F tilde composed of B to any other extension is A composed of the extension of F tilde composed of B. If A and B are Möbius maps. Okay, from the original definition we had of quasi-conformal maps, we have the distortion condition that the z-bar derivative of f is less than or equal to k times the z-bar derivative of f. So what this means the supremum norm of the difference of f sub z bar divided by f sub z is in fact an infinity. And in fact, in the unit form. Let's call it b of h of L infinity of h. So you see various notations for unit balls of L infinity. I'm going to use B, which stands for ball, and it also stands for Beltrami. So the complex dilatation which I might also call Beltrami coefficient or Beltrami differential, of a QC map F, let's just restrict it from the upper half plane to the upper half plane for the moment. Well, that is mu sub f is f sub z bar divided by f sub z, and mu of f lives in b of h, by what we observed up here. So just to go back to our example that we keep in the back of our mind, our affine stretch in direction k, then the complex dilatation of this thing is identically k minus 1 divided by k plus 1, which does indeed live in this number here. What a quite surprising result is that we can go the other way. So we start with a quasi-conformal map and we get an element of uniform of L infinity of H. Well, the measurable Riemann mapping theorem tells us we can go the other way. So if we start with some element in B of H, Well, we can solve the Beltrami differential equation f sub z bar equals mu of z f sub z and get a unique quasi-conformal map f upper mu from the upper half plane to itself, which fixes 3 points, let's say 0, 1, and infinity. Okay, this is only defined on H, but we know if you have a quasi-conformal mapping, it extends to R, and in fact infinity 2, so we can require that these 3 points are fixed. And the complex dilatation of f up mu is just mu. So what this tells us is that we can go back and forth between normalized quasi-conformal self-maps of H, so normalized to fix those 3.01 and infinity, and let's just say elements of the unit ball of n infinity of H. What I'm talking about here with Beltrami differentials, so elements of B of H and how they relate to QC mappings, that will probably come more to the fore tomorrow when we start talking about Teichmüller spaces and putting complex manifold structures on Teichmüller spaces. But for now, I'm just telling you stuff. Try and remember it for next time. So to finish, let's just do one or two more properties of quasi-conformal mappings themselves. Well, QC maps are not closed under addition. One of the great things about holomorphic functions is that you can add them and still get a holomorphic function. Not true for quasi-conformal mappings. Try and think of a simple example where this is true. But they are closed under composition. So you take one quasi-conformal map for the upper half plane to itself, and then another one, you compose them, and you will get another quasi-conformal map. So if F and G are quasi-conformal mappings from the upper half plane to itself, then F composed with G and G composed with F are, and the distortion of F composed with G is at most the distortion of F times the distortion of G. So the distortion typically will go up when you compose quasi-conformal mappings. It doesn't have to, like take G to be F inverse. But it still is bounded by some. And we'll also just say that the distortion of G composed of F is also bounded by K of F times K of G. So you can compute that the complex dilatation of, we got it, G composed with F. This has the following form, so it's mu sub F plus R sub F, mu sub G composed with F divided by 1 plus R sub F, mu sub F bar. mu sub g composed with f, where r sub f is f sub z bar divided by f sub z, so r of f has absolute value 1. So this kind of looks like a Möbius transformation, and you can take advantage of that when you want to try and prove things about the complex dilatation of compositions by sometimes appealing to the corresponding Möbius map properties that you get here. So for example, suppose we take our favourite affine mapping kx plus iy and square it. Well, this isn't quasi-conformal, but it's quasi-regular, and it's almost everywhere locally quasi-conformal. Well, then you can show that if you iterate this mapping n times, and you look at z, where z's in the positive real axis, well, this tends to 1, which is if and only if the distortion, well, how will I write this? Let's leave it like that. Actually, no, we can write that. We can say that this goes to infinity as n goes to infinity, and this is by taking advantage of the composition formula for Möbius mapping, so this equation here. So if you want some homework to do, if you don't want to sleep, then you can try and do this example to get a feeling for it. I'm not expecting anyone to do that. It's after 10, shall I call it a day for now? Okay, thank you for your attention.
Thank you, Alastair. Are there any questions?
Well, I have a question for you. Is this too fast, too slow? Okay. You get me for 3 more talks, so.
In the theorem you put the measurable Riemann theorem. What's the regularity?
Just that it lives in the unit ball of L infinity of h, so it's a measurable function, which is way nastier than how smooth the quasi-conformal mapping is. So that's why it's a sort of unexpected theorem that you can relate quasi-conformal mappings, which are differentiable almost everywhere, to something that lives in L infinity of h.
So the solution of the equation is the differential equation.
The solution is quasi-conformal, so it will, or you can construct it so it is quasi-conformal.
No more questions? No? Then if not, we thank Alastair again.